We need to understand the redox behavior of transition metals, and the specification has chosen vanadium for us to kind of illustrate this. Over on the far right, over here, I have written the instructions, the rules for writing half equations, which covered earlier, but I've just left them there, up there, in case you need to refresh your memory. It's a year 12 topic, really. Right, now vanadium can exist in a variety of oxidation states, ranging from +5 here down to +2, and you need to know the colors of those as well. Now it's quite a nice quite a nice experiment, and that's probably the best way to describe this experiment. And we can write the half equation and the half equations for the reactions involved. That's quite a good way of doing it. Right, so vanadium is usually supplied as ammonium metavanadate, which has this formula, NH4VO3. Sorry, there's no minus on it, but of course, what I'm going to say is that means it exists as the ammonium ion, which is spectator ion. I'm not going to do anything, and the VO3 minus ion. And you can see the oxidation state of vanadium in VO3 minus is +5. And then you dissolve that in acid solution. So the following reaction occurs. You get VO3, which is actually colorless, and add H+, and you form this yellow species, the it's called a dioxyvanadium ion, VO2+, and you're going to get a water as well. Okay, to balance that, we need to put a 2 there, and then we can see the charges balance on both sides, and everything else balances. You usually provide the H+ as sulfuric acid, so there's some sulfate spectator ions in there. So when you get this white powder, the ammonium metavanadate, you dissolve it in sulfuric acid, it turns yellow when you get the dioxyvanadium ion there. That's not a redox reaction, because if you look at the oxidation number of vanadium there, is +5, and here is +5, so no change in oxidation state. What you normally do then is you get a conical flask. I'll tell you why. It's easier to keep the air out of it. You get a conical flask rather than a beaker. You put your dioxyvanadium ion solution in there, so I'll do that in yellow. So it's the VO2+ in there, so that's yellow, and you put some zinc granules in there. And you make sure that this is dilute sulfuric acid, keep it acidified. And usually what you do is you put a piece of cotton wool in the top, so that lets, you'll make a little bit of hydrogen, because of course sulfuric acid reacts with the zinc a little bit and makes hydrogen. So that will let the hydrogen gas escape the cotton wool, but it tends to keep the oxygen out. And we need to keep the oxygen out for one of the later stages. So you heat that up. The zinc acts as a reducing agent, so the Zn will go to Zn2+ and 2-, so that's a reducing agent, and it will reduce the vanadium. So you start off with this yellow solution here, +5, and slowly it will start getting reduced to this blue one, the sky blue one, which is +4. It's a little bit confusing there, because when you do that, normally in between here, when you've got a mixture of the two, it will go green, and it's not this stage which is also green. So it goes yellow, then it goes green, then it goes sky blue when you've reduced it to the VO2+, the +4 oxidation state. You continue to heat it, and the blue gradually turns to this V3+, which is the green color. And if you carry on heating it, it will reduce it eventually to the V2+ ion, which is it's a pale lilac color. So it's really nice, colorful experiment. And this, for this stage here, that's why you need to keep oxygen out, because if you leave a solution of V2 plus just out on the bench, after an hour or so, it will turn green. It will turn back to the plus. The oxygen in the air can oxidize it to the plus. If you look at the redox potentials, we've done that. Oxygen is a strong enough oxidizing agent to turn V2 plus into V3 plus. So that's why you need the cotton wool in the flask here to keep the oxygen out. All right, so let's write some half equations for that then. Right, so the first one then, well, all the time we've got the zinc doing the reducing. I'll do that in a different color. So you've got the Zn, as I wrote before, goes to Zn2 plus and 2e minus. That's providing the electrons. Right, the first step, the VO2 plus. So we're going to get VO2, the dioxyvanadium ion, and that will go to this sky blue VO2 plus, and it's very confusing because it sounds the same, VO2 plus and VO2 plus, but they're different. The two is in a different place. You see what I mean? So that reduces it. So what we've done there, we've balanced for the element of interest. We don't need to worry because we've got one vanadium atom. Now we need to balance oxygens for H2Os. So I have got 2 on the left and 1 on the right. So I need an H2O here, which means I need 2 protons here. That's step 3, balance the hydrogens with H plus. Finally, balance the electrons, the charge with electrons. So I've got a total of 3 pluses on the left and only 1 plus, 2 pluses on the right. So I need 1 electron in there. If you wanted to check the oxidation numbers and make sure everything's okay, yeah, that's fine, because this is plus 5. This is plus 4. So it's being reduced by 1 electron, and we're gaining electrons, so that's good, and there's only 1 of them, so that's all right. That's fine. The next step then is to reduce this blue dioxide, the blue vanadium 2 plus, VO2 plus, and that's going to go to the green V3 plus. Right, first of all, balance element of interest, 1 vanadium, so we don't need to worry there. Oxygens, well, we need another H2O on the right. Step 3, balance for hydrogens, we need 2H plus again on the left. Charges, well, we've got plus 4 charges on the left and only plus 3 on the right, so we need 1 electron. Check the oxidation numbers. We're going from a plus 3 oxidation state, sorry, plus 4 to a plus 3, so it should be 1 electron, and the electron should be gained, and it is, so that's all right. The last step then is for to reduce it further to V2 plus. So that's the one where we need to keep oxygen out of the way for it. So we have V3 plus there, and that is going to go to V2 plus. We don't need any balance element of interest. We've done that. No oxygens, no hydrogens, just balance charges. So we want 1 electron on that side. And we've got it all the way down to the plus 2 oxidation state. So what you can do then is, when you've done that, is, so you're going to end up with a flask with your lilac V2 plus solution. So you've got a flask with your violet V2 plus solution, and you've got some zinc in there as well. And you've got bits of zinc. Well, what I like to do is decant this way. You've got to get away from the zinc, from the reducing agent, because what we're going to try and do is we're going to oxidize it back up to the plus 5 state. So you need to get away from the zinc, which is a reducing agent. So decant that into a beaker, and you'll have a nice lilac solution there. Now, if you just leave that on the bench, and you can help this by if you give it a little stir just to get the oxygen towards it. Yeah, you just leave it for a few minutes. You'll find that the oxygen will turn it into the green V3+. So let's write a half equation for that. So we've got oxygen, it's the oxidizing agent, and that's going to get reduced because it's acting as an oxidant. It will go to water. Balance of the element of interest. Right, this is a bit tricky with oxygen because the oxidation number does change the oxygen in this half equation. So we've got to put a 2 there. Right, balance for O's with H2O's. We don't need to do that as we're dealing with oxygen. Balance H with H+, so we need 4H+. Balance the charges. Well, we've got 0 charge on the right and +4 on this side, so we need 4 electrons there. And if you wanted to, you could combine that with the V. You know what's happening here. We've got V3+ going to, sorry, V2+. That should be, sorry. V2+ is being oxidized to V3+. So we need an electron. There's losing an electron there. And you could combine these two. You'd have to multiply the bottom one by 4 to write a full equation there. So if you just leave it in air, that's the oxygen is unable to oxidize it any further than V3+. So if you want to do it backwards, well, what you normally do then is to add another oxidizing agent, potassium manganate 7 or potassium permanganate. So get a beaker of potassium permanganate, which is a dark purple stuff. Okay, you don't need to acidify it because you'll have plenty of acid in there already. So here's our dark purple KMnO4. It's only the manganate ion that we're interested in. Of course, the potassium ion is just a spectator ion, so we can forget about that. We need to write a half equation for manganate. So manganate goes MnO4, and this is a really important one to remember, this part of the spec. It will get reduced to the Mn2+ ion. Now this is purple, and this is colorless. So what happens? Well, let's balance it. So we need 4 H2O's on that to balance for the oxygens. Then we need to balance for the hydrogens. We need 8H+. Balance for charges. We've got 7+ on the left and only 2+ on the right, so it's 5 electrons. We check our oxidation numbers there. We've got +7 state for manganese there, and +2 there, so it should be 5 electrons. So if you get some of this stuff and you pour it into the vanadium, what happens is that green will start, this green here will slowly start turning into that nice sky blue color here, the VO2+ ion, and then keep adding a little bit more, just add a bit of manganate at a time. And of course, what happens is the purple color of the manganate disappears because it turns into this Mn2+ ion, which is colorless. Add a little bit more, and you'll eventually make it go yellow again. Okay, and you oxidize it back up to the +5. And then if you added any more manganate, then there'll be nothing to reduce the manganate, so that purple color would then persist in the beaker. So it's a nice colorful experiment, and it's on the spec. You've got to know all those changes, and you've got to be able to manipulate all those half equations. So it's good practice to get all those, write them all out yourself, and basically go through this video so you know it all without looking.